Okay, so we have a ergodic theory practice final exam. Let's begin. Number one, let X B script mu be a probability space, and let T map X into X be measure producing. And what we need to show is for part A, show that the integral of F of composed with T d mu is equal to the integral here of f d mu for every f, okay, in L1 x mu. Okay, so let's see here. This is a measure preserving transformation problem. Since t is a measure preserving this mu of t inverse A equals mu of A for every measurable set A. We're going to prove this statement for indicator functions. We're going to let f equal the following at 1 sub A. So we have this composition here for this integral, this 1 sub A composed with t du, and that equals mu of t inverse A equals mu of A equals this integral of that 1 sub A d mu, which is that f. And by linearity, the result holds for simple functions. We could say that any non-negative measurable function can be approximated by simple functions. So now from here, what we're going to do, we apply the monotone convergence theorem. Okay, we have this integral here of f composed with t d mu, and that equals the integral of f d mu. And for that general L1 functions, we write f equals f plus minus f minus, and applying the previous result separately. So the integral here of that f composed, integral of f composed of t d mu, composed with t d mu, equals the integral of that f d mu. Okay, so that's for part A. Sorry, I'm having some trouble with allergies. Part B, show the Koopman operator, UF equals that F composed with T, defines an isometry on that L2 X of X mu. Okay. So what we do here is we compute this norm UF squared. So that norm UF sub 2 squared equals this integral here of that absolute value of F composed with T integrated along d mu, and then applying information from part A, this absolute value of that integral of f composed with t d mu equals the absolute value of f squared d mu. So we could say here this norm uf sub 2 squared equals the norm f sub 2 squared. And if we take the square roots here, that norm uf sub 2 equals norm f sub 2, and thus showing that u is an isometry. Okay, so that's number one. Let's move along to number two. Okay, so number two, let t of x equal x plus a bod 1 on this circle where t equals r bod z, where alpha is irrotational. Show that t is ergodic with respect to Lebesgue measure. Okay, so irrotational rotations problem. So we suppose that f belongs to L2 of t, satisfies that f composed with t equals f, and expand in this Fourier series given here for that f of x. So then we could say f of x plus alpha equals the following when we substitute in for that x plus alpha goes in, And now we could write it as this sum of C sub n equals e to the 2 pi n alpha e to the 2 pi I n x. And since f of x plus alpha equals f of x, this c sub n e to the 2 pi I n alpha equals c sub n. And rearranging this and factoring, we get c sub n times the quantity e to the 2 pi I n alpha minus 1 equals 0. And because alpha is irrational here, e to the 2 pi I n alpha cannot equal 1 for every n cannot equal 0. Therefore, c sub n equals 0 for all n cannot equal 0. Sorry. Only c naught survives. So f is constant almost everywhere. And by the invariant function characterization of ergodicity, sorry about that, T is ergodic. Sorry if I mispronounce anything. Voice is very scratchy from allergies. Sorry. That's number 2. Number 3. For number 3, we assume T is ergodic. Let f be L1 x of mu and show that this limit n approaching infinity 1 over n for this sum n equals 0 to n minus 1 for f of t to the n x equals that integral f d mu for almost every x. Explain carefully why ergodicity is needed. So Birkhoff's ergodic theorem application. So Birkhoff's ergodic theorem states this: a sub n f of x equals 1 over n, then the sum n equals 0 to n minus 1 f of t to the n x converges almost everywhere. We're going to let f star of x equal limit n goes to infinity a sub n f of x. The theorem is going to further state that f star is t invariant. Since t is ergodic, every invariant function is constant almost everywhere. Therefore, f star of x equals c. Integral of f star equals c, and c equals the integral of f d mu. So the limit as n approaches infinity, a sub n f of x, that equals the integral of f d mu for almost every x. And we could say for that part, we're good. And for this explanation, ergodicity is needed. Without ergodicity, f star need only be invariant, and invariant functions need not be constant. Thus, the limit may depend on the starting point, x. Okay, so that's number 3. Moving along to number 4. Suppose t is mixing. We have mu of t, the negative n, and that a intersect b, and that's going to u of a, u of b. Okay, or converges to u of a, u of b. Show that t is ergodic. Mixing implies ergodicity, so we can let a be invariant in that t inverse a equals a, and then t to the negative n a equals a for every n. So mu of t to the negative n a intersect a equals mu of a. And by mixing that mu of t to the negative n a intersect a, that's converging to u of a squared, or going to u of a squared. Therefore, u of a equals mu of a equals mu of a squared. And thus mu of a times the quantity 1 minus mu of a equals 0. So mu of a equals 0, or mu of a equals 1. And this is precisely ergodicity. Mixing implies ergodicity. So, or mixing implies ergodic. Okay, moving along to number 5. Bernoulli shift. So for number 5, consider x equals the following. So for this with product measures here given, okay, and let's see what we have. Define Tx sub n equals x sub n plus 1. Show that T is measure preserving. So this is Bernoulli shift. We consider a cylinder set given here. Sorry. This set of x such that. And its measure is mu of c equals 2 to the negative m. That T inverse of c equals this x such that. Okay. And this is another cylinder set with the same number of specified coordinates. And therefore the mu of that T inverse C, that equals 2 to the negative m. Hence that mu of T inverse C equals mu of C. And cylinder sets generate the sigma algebra. Therefore mu of that T inverse A equals mu of A for all measurable A. So I just went over these rather quickly so you have them as a reference, and that's part 1 through 5. Thank you, and have a great day.